Namaste students, welcome back to Rama Teaches You. Today we are going to do the third video on chemical bonding and molecular structure. Okay, and this is going to be the English video. So in the previous video, we ended the class with ionic compounds. Okay, so ionic compounds, their structure, their properties, we had finally done a couple of properties which were, let's say, we had the physical state, they were usually solids in nature, high melting and boiling point compared to the covalent molecule. Why? Again, because their structure is made up of what? It is made up of an electrostatic force of attraction. So it has a higher the force between them, the bond between them is stronger than compared to a covalent molecule. That's also we discussed in the last class. Then solubility. So we know that the ionic solids, ionic crystals do have a polarity. What does that polarity mean? They have every single unit has a positive charge and a negative charge, that is a cation as well as an anion, and so we call them polar molecules or ionic compounds. Similarly, we have certain solutions which are also polar in nature. For example, the H2O molecule. H2O molecule is a polar molecule, right? So because of it has two centers of charge. You have the positive charge on hydrogen and you have the negative charge on oxygen, right? So in a polar molecule, it becomes easy for the ionic compound to dissolve. That's where the saying comes from, like dissolves like. Okay, next we were going to start with electrical conductivity. Okay, so ionic solids on their own are not electrically conductive in nature. See, what is required for electricity's conduction? You need some charge to move, right? What is current? Current is defined as a moving charge. A moving charge is called current. So, what we need is some sort of a moving charge. Okay, now in an ionic crystalline solid, the cations and anions are fixed in their own position. They may or may not have free electrons, that's a whole different story. But in the crystal lattice, they are all arranged in such a way that they don't move, they are basically fixed. Now if I were to take that same crystalline solid and melt it by heating its temperature or by dissolving it in water, what do I see? I see that suddenly the ions have separated themselves, right? Due to which what happens, now you have free moving, free flowing ions in a solution, and that particular reason is alone responsible for the conduction of electricity. Okay, so ionic compounds are good conductors of electricity in their aqueous state or molten state because of the presence of free ions in these states. However, they do not conduct electricity in their solid state because of the absence of free ions, as strong electrostatic force of attraction binds these ions. Right? The electrostatic force of attraction is huge. It is a very huge compared to that of covalent molecules. So usually they don't have any free ions with them. Okay, now next, ionic reactions. Now see, if you take an aqueous solution or a molten solution, because the ions are already disassociated. Drupad, could you please explain to me what disassociation means? Yeah, exactly. Basically, you don't need to have an anode or a cathode, Drupad. Dissociation could happen even in the absence of electricity. For example, if you just put some ionic solid in water, it will hydrolyze itself. It will dissociate itself into, for example, let us take the example of sodium chloride. It would dissociate itself into sodium and chlorine ion, sodium Na plus and chlorine Cl minus. So that is what dissociation means. Okay, since they are already in their disassociated state, it becomes easy for the reaction to take place as compared to a covalent molecule. Because in a covalent molecule, even if you dissolve it, its bonds don't break. Okay, so for if you want a reaction to take place, you have to wait for the bond to break. So that's why a covalent reaction, a covalent bond reaction is less faster or slower as compared to that of an ionic reaction. For example, NaCl, you can see this. See, Na plus NaCl, sodium chloride. How have they shown it here? They have shown it like this. Sodium is its own ion, chlorine is its own ion, silver is its own ion, nitrate is its own ion. So basically, this and this can combine quickly to produce sodium nitrate and silver chloride. Okay, now the non-directional characteristics. What is the non-directional characteristic? I think we discussed in this in yesterday's class too. So a non-directional characteristics means basically the ionic bond is non-directional. This is because each ion is surrounded. For example, in the case of sodium chloride, sodium is surrounded by six chlorine ions, right? One here, one here, one here, one here, one top, one bottom. Okay, so basically there are six chlorine ions surrounding a sodium ion. Similarly, there are six sodium ions surrounding a chlorine ion. So the pull that the sodium and the chlorine ions face is equal in all directions. So basically, all the directions like pull from here and pull from here gets cancelled. Pull from here gets cancelled. Pull from the top, pull from the bottom gets cancelled. So there is therefore zero directionality. The directionality becomes zero. Understood? That is what directionality means. The formula of an ionic compound can be easily written by knowing the valency of the combining atoms. Okay, for example, barium chloride. Barium has a valency of +2, chlorine has a valency of -1. So basically, every barium cation can accommodate two chlorine anions. Therefore, you will have the formula BaCl2, barium chloride. Okay, any doubts till now? No, right? You got doubts? Okay. Now, the bond parameter. The various characteristics shown by bonds. Yeah. So the next topic that we have to discuss is the bond parameter. Okay. Now, the various characteristics shown by bonds are called the bond parameter. These are as follows. The first bond parameter, this could be considered as characteristics or features. When we talk about something, there are some features, right? Or some characteristics. So in the same way, we have something known as the parameter. So in what parameters does the bond actually fall in? Now, the first one is called the bond length. Now, the equilibrium distance between the nuclei of two bonded atoms is in a molecule is called the bond length. It is measured by a spectroscopic X-ray diffraction and electron diffraction techniques, and it is expressed usually in angstroms. The reason why we created this unit called angstroms is because most of the bonds in a chemical in a molecule usually end up in the ratio of in the range of 10 to the power minus 10. Okay, that is the reason why we have angstroms in the first place. Okay, so basically, you can use an electron microscope. You can use an X-ray spectroscope. Basically, the diffraction that an X-ray does on or a reflection that an X-ray does on the bond allows you to measure what the distance between the two bonds will be. Okay, next. It is measured as the radius of an atomic core which is in contact with the core of an adjacent atom in a bonded situation. So basically, in simple words, instead of saying the core, we can usually say the nuclei. Atom's core is nothing but the nucleus. So the nuclear distance between the two atoms that are being combined together will be known as the bond length. Okay, from the two centers, the distance is known as the bond length. Okay. In a covalent bond, the contribution from each atom is called the covalent radius. It is equal to half the distance between two similar atoms combined together by a covalent bond in the same molecule. What does it mean? For example, if you have a hydrogen bond here, hydrogen molecule, like look at this. Sorry. Mm, yeah, this is what a hydrogen molecule. So what are they saying? What is a covalent radius? It is half the distance between two atoms. Half the distance between two atoms in a molecule which has both the atoms of equal nature. That is, you need to have a hydrogen here and you need to have a hydrogen here. So basically, half the distance would be the covalent radius. Understood, Drupad? Any doubts here? Did you understand the covalent radius? Okay. Okay. Bond length. The bond length is given as Ra plus Rb. That is the bond radius of this one plus the bond radius of this, sorry, the covalent radius of this one plus the covalent radius of this one will give you the bond length. Okay. Now, the covalent radius Ra is equal to Rb is equal to d by 2. Here, Ra and Rb are the covalent radii of the two atoms A and B respectively. The van der Waals radius. Now, this is a pretty simple concept, right? So, basically, if you want to find the covalent radius of hydrogen, what will you do? You will write Ra 2 Ra upon 2. This basically, this distance upon 2 will give you the bond radius, hydrogen radius, or the covalent radius of hydrogen. Okay, so it's a pretty simple concept. We are not learning something crazy or anything. Okay, now Rb is equal to d by 2. Okay, one second. So the next concept that we have to learn is the van der Waals radius. Okay, now we know what is a van der Waals bond, Drupad? Can you explain to me what a van der Waals bond is? Do you remember van der Waals bond, Drupad? Yeah, yeah, but then what is a covalent bond? That's also an attraction between atoms. Okay, see, now, yeah, but the how do you explain this? You explain it like this: a van der Waals radius, a van der Waals bond is a bond that exists between two intermolecular or interatomic species. Okay, so it's not between two atoms. That's where you are wrong. Okay, usually what happens is you see van der Waals radius between two molecules. Okay, you could be, you are partially correct if you take the examples of helium, neon, argon, krypton, xenon, and radon. They have, you can call them as atoms between two different atoms. But in the case of majority of the species that you see there, you have to use the word molecules. Okay, atoms and molecules, two molecules that are separated by a distance. They don't share anything between each other, they don't transfer anything between each other. What that you said is correct only, but they have a certain type of influence between each other. Okay, that is known as the van der Waals radius, van der Waals bond. For example, there exists van der Waals bond between the two layers of a what do you say, graphite. Two layers of graphite, there is a van der Waals bond, right? We learned that in carbon and its compounds, class 10th. So, the radius represents the overall size of the atom, including its valence shell in the non bonded situation. It is equal to half the distance between two similar atoms in separate molecules in a solid. Okay, so basically, the distance between two similar atoms, that is oxygen on oxygen, in the case of two oxygen molecules separated by a certain distance, the van der Waals radius of this is van der Waals radius. Look at this. This whole thing is called the van der Waals radius. So basically, you need to have two similar atoms. Okay, two similar atoms in two different molecules. The distance that is between them is called the van der Waals radius. The covalent and the van der Waals radius of chlorine are shown. See, this is known as the covalent radius, right? This is the chlorine molecule. This is also Cl. This is also Cl. So the distance between the distance between the two chlorine atoms is this much. So half the distance is this much. Therefore, you have something known as the covalent radius. Similarly, you have the van der Waals radius. This whole thing is the van der Waals bond length. Okay. Therefore, the van der Waals radius will be half of this much. Two similar atoms. This has to be chlorine and this has to be chlorine. The distance between two similar atoms in two different molecules. Two similar atoms, that's the key point. Two similar atoms between two different molecules is called the van der Waals radius. So, Rc represents the covalent radius and VDW represents the van der Waals radius. Okay, you have the covalent radius and the van der Waals radius. Okay, now can I say with absolute certainty that the covalent radius RC will always be less than R VDW, van der Waals radius. It's correct, right? See, basically the space, yeah, that is that it's always going to be like that. You're always going to get the covalent radius to be much more lesser as compared to the van der Waals radius. Now, the next topic, the various factors that affect bond length are as follows. Si- uh, the sign of the atoms. The bond length increases with the increase in the size of the atoms. Thus, the order of bond length of HX bond is HF is less than HCl is less than HBr is less than HI. So it's easy, right? See, basically, the fatter the atom is, the more distance there will be between the two nuclei of the atom, right? See, understood. So basically, like if a huge ball and a small ball are basically kept next to each other, the distance between the two centers of the two spheres will increase because the size is increasing, right? So similarly, the carbon carbon bond is less than the carbon silicon bond and the germanium germanium bond, even though all of them kasi gaye. So basically carbon silicon and germanium belong to the same group, but as the actual size of the atom increases, the bond length also absolutely increases, right? It will also increase. Now, the next type is bond multiplicity. The bond length decreases as the multiplicity of the bond increases. Okay, now think about this. See, why does a bond actually form? It forms due to the overlap of the orbitals. That is what you're going to see in the next topic. That is the Vesper theory. Usually, what happens is that there is an overlap taking place between the two. There is an overlap taking place between the two atoms. Okay, the orbitals of two atoms. Now, the more overlap you have, the lesser distance you will have. It's like this. See, if I can hold you with one hand, if both our hands just meet in one place, okay, we are both holding together with one hand, then our length is huge. Like basically, we can spread our full body. But if both our hands are holding together, then the gap between us actually reduces, it actually decreases. So, the more the number of bonds you have, the lesser will be your bond length. So, for example, a triple bond will be the shortest between two atoms, similar atoms, compared to that of your double bond and then a single bond. Single bond will have the highest length. Now, the bond length also increases as the p character increases. So, this is something that you're going to learn pretty soon. What is sp, sp2 and sp3? These are known as hybridization. In structure of an atom, you had dealt with the various kinds of subshells and orbitals that you have. You have the s, you have the p, you have the d, and you have the f, right? We have already discussed these things. Now we are going to see the bond that is formed actually does not take place by a single orbital alone. You need to have multiple orbitals. You need to have hybridization of orbitals. Okay, hybrid orbitals are the ones that actually participate in the bond formation. Okay, and that it's not a rule, because there are sometimes you have s orbitals overlapping each other. No, I'm not going to discuss this right now. As soon as we enter the Vesper theory, I'll explain to you even more clearly. Okay, average bond length for some single, double, and triple bonds. Look at this. The OH bond has a bond length of 96 picometers. Now let's see a triple bond. Does this have a triple bond? CN. Is there a triple bond here? No, there's only a double bond here. Okay, no problem. But do you see that the bond length is actually increasing as the size of the atom increases, and as the bond length decreases as the double bond or a triple bond is formed between the two atoms. Did you understand this whole section, Drupad? Okay, shall we move on? Okay, next, the bond angle. Now, in the Lewis dot structure, the thing that always amazed me was that it was a stick figure, right? You had carbon, hydrogen, 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 hydrogen. basically a two-dimensional diagram. Okay, that's not how a molecule actually looks. Okay, so basically there is something known as a lone pair electron and a bond pair electron. An electron that participates in the formation of a bond is called a bond pair electron, whereas an electron that participate that is not participating in any bonds, it is just simply staying inside the atom, you get an lone pair of electron. Okay, the angle between the orbitals containing the bonding electron pair around the central atom in a molecule or a complex is called the bond angle. It is expressed in degrees, which can be experimentally determined by a spectroscopic method. Bond angle gives some idea about the distribution of orbital compound or around the central atom in a molecule, and hence help in determining the shape of the molecule. It also gives us some idea about the lone pair of electrons, as more number of lone pair of electrons, lesser is the bond angle. Now I'll explain this to you in simple words. Okay, so let's look at this. Drupad, could you please tell me how many electrons are present in the valence shell of carbon? Four. Okay, so there are four electrons like this, and there are six electrons present in oxygen. Okay, there is an overlap taking place here, and there is an overlap taking place here. Okay, there is an overlap taking place like this also. Okay, this is the structure, the Lewis dot structure of carbon dioxide. Now, when we draw this, we can draw it like this. This is nothing but a straight line. The angle between the two oxygen atoms is actually 180 degrees. Now, CO2, CO2. Okay, this is the structure of carbon dioxide. Now, I'm going to draw H2O. Now, both of them have three atoms, right? Both of them have three atoms. But let's look at the structure of oxygen. This is how an oxygen molecule looks like. Okay, now, do you see what is happening here? Carbon did not have any lone pair of electrons around itself, but the oxygen does. So, when there is a bond formation taking place, this this lone pair of electrons and this lone pair of electrons, they repel each other. Due to which, what happens? A molecule that was supposed to look straight, because of this repulsion of these two electrons, it is bending this molecule like this. It is literally bending it, and this molecule's shape is also known as bent shape only. Okay, so oxygen, hydrogen, hydrogen. So there is actually an angle that is present between the two successive bonds. This is known as the bond angle. Understood this? So ideally speaking, it should have been a straight line, but because oxygen has lone pair of electrons and carbon does not have a lone pair of electrons, what happens? Oxygen is forced to bend its bonds so that it becomes a bent shape. Understood? So this is how bond angle actually works. Shall I move on? Okay, let's move on next. So, for example, HCH bond angle in CH4, HNH bond angle in NH3, HOH bond angle in H2O, and FBF bond angle in BF3 are shown in figure. So, oh my God, the scan did not go well. Um, this is 109 degrees, 28 minutes. Um, do you have the book open in front of you? This is 120 degrees. Okay. What is the bond angle of H2O? 108 something, 104.5. And what about ammonia? Okay. So you have one lone pair of electrons, you have two lone pair of electrons, and there is no lone pair of electrons. Now, in the CH4 molecule, that is methane, there is no lone pair of electrons. So the bond angle usually becomes 109 degrees 28 minutes. Now it's a tetrahedral structure. Okay. So this is what in the ninth in 10th class, carbon and its compounds, you learned a concept known as tetrahedral in diamonds. Basically, when one carbon is surrounded by four other carbons like this shape, this arrangement of the structure, we called it a tetrahedral structure, right? Okay, so let's move on. Now, this is no bond angle. This is called a trigonal planar structure. You're going to learn more about this in the valence shell electron pair repulsion theory. This is all part of that only. Next, if there are four bonding domains, uh, uh, the bond angle is 109 degrees 28 minutes. But if one of the domain is a lone pair, bond angle is less than 109 degrees 28 minutes. If there are these bonding domains, bond angle is 120 degrees. And if there is only exactly two bonding domains, bond angle is 180 degrees. Okay, so basically that is this 180 degrees is the case of carbon dioxide. Okay, but if there is a lone pair present, the angle will be less than 180 degrees. That is in the case of water. Okay, okay, let's move on. Now, the various factors that affect the bond angle are as follows. The bond angle decreases with the decrease in the S character. Okay, that if the S character decreases, the bond angle actually decreases. Okay, similarly, the bond angle is affected by the presence of lone pair of electrons. Lone pair repulsion decreases the bond angle. So, ideally speaking, H2O was supposed to have a bond angle of 180 degrees, but because of the two lone pair of electrons that are present in the oxygen atom, sorry, in the oxygen atom, the bond angle actually reduces to 104 degrees and 5 minutes. Okay, so this is how the bond angle is affected. Okay, now we learned about the bond length. Now we also learned about the bond angle. Okay, next, predict all the bond angles in these molecules. CH3Cl. Okay, CH3Cl is a tetrahedral structure. Okay, because carbon does not have any lone pair of electrons, so one hydrogen, one hydrogen, and one chlorine, all of them basically take the four positions of carbon. So each and every single angle will be equal to 109 degrees and 28 minutes. We will learn more about this in the next section. Now, the Lewis, what about the next one? CH2, predict all the bond angles in the molecule. You have H2 double bond CHCl. Okay, the Lewis structure for CH2 CHCl is this. Now, basically, carbon is surrounded by three different types of atoms, right? This carbon is surrounded by one hydrogen, and one carbon. This carbon is surrounded by one carbon, one hydrogen, and one chlorine. So basically, if there are three atoms present around a central atom, see right now the central atom is carbon. Carbon is surrounded by three different types of atoms. So the bond angle will be 120 degrees. It literally looks like this, Rupert. See, the angle between the three has to be the same. It's all of this is lying in the same plane. Okay, now if this is also x, this is also x, and this is also x, Drupad, then this x plus x plus x, x plus x plus x should be equal to 360 degrees. 3x should be equal to 360 degrees. X should be equal to 120 degrees. That's how we are getting 120 here, 120 here, and 120 here. Understood? Any doubts here, Drupad? See, this is the central atom. Central atom. This is the central atom. Let's move on. Okay. Bond enthalpy. The amount of energy required to break a bond. Okay. Break 1 mole of a bonds is called in a particular type between two atoms in a gaseous state is called its bond enthalpy. Okay. You are going to break 6.022 into 10 raised power 23 bonds in a molecule. You get the bond enthalpy. It is the amount of energy required. It is the amount of energy required to break 1 mole of bonds of a particular type between two atoms in a gaseous state. Okay, both of them have to be in the gaseous state. This gaseous state is a very important name. You have to remember to write the gaseous state. The unit of bond enthalpy is kilojoules per mole. That is, the hydrogen iodine bond enthalpy in the hydrogen molecule is 435.8 kilojoules per mole. So basically, if you want to break 1 mole of Hi bond, you have to break 1 mole of this Hi bond you are breaking. You will require this much amount of energy. Now, we know that delta H, if delta H, what is delta H, Drupad? I have taught you this in structure of atom. What is delta H? H means what? Enthalpy. It is heat only, but it is the enthalpy is the actual term. Okay, you will learn more about this in thermodynamics. Okay, enthalpy. Okay, enthalpy. Now, if delta H is positive in chemistry, if delta H is positive, it means the heat has to be supplied in. If delta H is negative, then the heat will be released. No heat has to be supplied. Okay. Now, note, larger the bond dissociation enthalpy, stronger will be the bond in the molecule. Okay, the more the bond, see, it's like this. You have two sticks. Okay, if one is made up of wood, the other is made up of metal. Okay, so one will be easy to crack. The wooden stick would be easy to crack, right? But the metal stick, it will be a bit difficult. You will be able to crack it. If it is thin enough, you will be able to crack it, but it will require more effort from your side, right? Why? Because the other stick is actually pretty strong. So we can say that if a bond has a higher bond enthalpy, indirectly it is saying that it is strong. The bond is very, very strong. You require more effort to break it. If you require more effort to break it, then that stuff is pretty strong. That is the correlation that I want you to observe in these two statements. Did you understand this? The stick and the bond? Very good. Next. In case of diatomic molecules such as H2, O2, N2, and HCl, the bond enthalpies are equal to their dissociation enthalpies. Now, what is bond enthalpy? It is the amount of energy required to break 1 mole of your 1 mole of bonds between two atoms in a molecule. Similar bonds. Now, what is your dissociation enthalpy? Again, you are separating a bond, is separating a molecule into its in constituent atoms. You are dissociating it. So, if you have only two atoms, if you have only two atoms in a molecule, one second. So, if if the two atoms, if there are only two atoms present in a molecule, the dissociation enthalpy will be equal to its your bond enthalpy. Understood? Because there is only one bond present inside the molecule. Now, and hence have fixed values. While in the case of polyatomic molecules, a particular type of bond is present in different molecules. For example, the OH bond in OHO or CH3OH, or even in the same molecule. For example, the four carbon hydrogen in CH4 do not possess the same bond enthalpies. What they are trying to say is, see, you have the O, H, and H here. You have the C, H, 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 H. So you may think that this bond and this bond possess the same amount of energy. That is, the amount of energy required to break them will be the same, but you will be dead wrong. That is wrong. That is absolutely incorrect. Similarly, all the four bonds will have different energies. Now I'll let you know why. See, what happens when you break this OH bond? What do you think happens, Rupert? In your own words, please let me know what happens as soon as this bond is broken. What do you think? What will happen? Yeah, but that is. Is there anything else? Is there anything else that will happen? See, basically, I'll let you know. See, when you break the first hydrogen atom, okay, oxygen panics. Oxygen goes into a panic and it holds on to the other hydrogen atom even more tightly. Okay, I'm giving the molecules emotions so that becomes easy for you to understand. Oxygen panics and it holds on to the hydrogen atom that is next to it even more tightly. Therefore, the next bond enthalpy will be even higher. Understood? That's what's happening here. Now, a particular type of bond, yeah, do not possess the same bond enthalpy due to different electronic environments. Hence, the bond enthalpy are usually the average values and are called mean or average bond enthalpy. So, let us imagine that the this bond to break this bond, the bond enthalpy required was delta H1, and for to break this bond it was delta H2. So the bond enthalpy of hydrogen of water will be delta H1 plus delta H2 upon 2. It will be the average of these two. Okay, it will be known as the average of these two. In the H2O, the first OH bond enthalpy is 502 kilojoules per mole once, and the second bond enthalpy is 427 kilojoules per mole once again. I'm so sorry about this. I was thinking about electron, the ionization enthalpies. Okay, here actually what is happening is the first OH bond is more stronger compared to that of the second OH bond. Okay, hence the average bond enthalpy 502 plus 427 upon 2, you get this value. This becomes the average bond enthalpy. Okay, I was thinking about electrons. I'm so sorry about that. Now, a more detailed study of bond enthalpy will be given in chapter 5. Several factors that affect the bond enthalpy are: number one, the size of the atom. The greater the size of the atom, the greater is the bond length, and hence lesser is the bond dissociation enthalpy. Lesser is the bond length. Now, I want you to imagine like this. Drupad, is it easy to break a longer stick or a shorter stick? Is it easier to break a longer stick or a shorter stick? Why? You have more of a leverage, right? You have more leverage when it comes to a longer stick. Okay, but when it's a small stick it becomes really easy, it becomes really difficult to break it. Now something similar is happening here also. The more the distance between the two atoms inside a molecule, the more is their bond length. Okay, and as the bond length increases, the distance between the two nuclei also increase. Okay, so bond is being formed by the attraction of one nuclei with the other's electrons and the other's nuclei with the first electrons. Okay, now if you increase the distance, the force of attraction that these have, okay, it will get reduced to a very large extent. The electrostatic force, okay, it's a form of attraction only. The even overlap is basically a certain form of attraction. Now what is happening here is, as the distance increases, this attractive force actually reduces its strength. Therefore, what ends up happening? They are not as tightly held together as compared to molecules having smaller atoms. Okay, therefore, as the bond length increases, because the size of the atom is increasing, the bond length is increasing, therefore, the attractive force that is existing between the two is decreasing, and therefore, the bond enthalpy. Okay, the bond enthalpy decreases. I hope you understood this. Did you understand this? Yeah. Now, the bond multiplicity. Greater the multiplicity of the bond, greater is the bond dissociation enthalpy. This is because atoms come closer and the number of bonds to be broken is more. The bond dissociation enthalpy of H2, O2, and N2 follow the following order. All of these are bimolecular in nature, right? They are bimolecular species. Sorry, uh, yeah, no, wait, not bimolecular. Diatomic species. All of them are diatomic species, right? So basically, even though they are diatomic, the only difference that there exists is that hydrogen has only one bond, the oxygen has double bond, and the nitrogen has triple bond. So the triple bonded nitrogen will have the least distance between the two, and hydrogen will have the most distance between the two. Therefore, the bond enthalpy of hydrogen will be lesser as compared to that of the nitrogen molecule. Okay, the next, number of lone pair of electrons. Greater the number of lone pair of electrons present on the bonded atoms, the greater is the repulsion between the atoms, and hence lesser is the bond dissociation enthalpy. Okay, so the greater the number of electrons you have, more repulsion you have. Okay, greater the lone pair of electrons present, the bonded atoms, greater is the repulsion. So two atoms, if they want to form a bond together, they have to be close enough. Okay, so but if there is a repulsion that is happening between the two electrons, then what happens? Due to this repulsion, the distance between the two increases. Therefore, the as the distance increases, what happens? As the distance increases, the bond length increases. Therefore, the bond enthalpy decreases. Extent of the overlap. Higher the extent of overlapping, stronger is the bond and higher is the bond length. This overlap is something that we are going to learn in Westcott theory. Okay, for now, just remember it that more overlap you have, the more bond enthalpy you will have. Okay, next, the bond order. Okay, what is the order of a bond? In the Lewis description of covalent bonds, the number of bonds formed between two atoms in a molecule is called the bond order. For example, the bond order of a hydrogen molecule is how much? The bond order of a hydrogen molecule is 1. The bond order of oxygen molecule is 2, nitrogen molecule is 3, carbon and oxygen molecule is 3. So basically, the number of bonds that is being formed becomes equal to the bond order. Now, in case of odd electron molecules, Drupat, what is an odd electron molecule? What was an odd electron molecule? Here. Yes. So, odd electron molecules like NO, NO2, and O2, etc., are examples of some molecules in which the bonded atom have odd number of electrons, usually 3 in between them. Okay, if you have 3 electrons in between them, then that's why they are called odd electron molecules. Okay, odd number of have odd number of electrons in which bonded atoms have odd number of electrons between them. So Drupad, where were we? Yeah, so in the case of NO, how many electrons are present in between them? How many electrons are present between them in this odd electron molecular formation? 1, 2, 3. Yeah. So something, it's an odd number, right? So in case of odd electron molecules, the three electron bonds are considered as equivalent to half a covalent bond. Thus, bonded order can be a fraction also. Okay, what did you understand from this? If in the case of odd electron molecules, the three electrons bonded are considered as equivalent to half a covalent bond. The three electrons that are bonded can be considered as half a covalent bond. Thus, the bond order can be a fraction as well. So this becomes the number of bonds that are present here is 2, right? There are two atoms present here, there are two bonds present here. So 2, 1 by 2. Okay. So you can have half. It can be considered as a fraction as well. Next. In case of isoelectronics molecules and ions, the bond order may be identical. For example, F2 and O2 minus have bond order 1. N2 and CO and NO plus have a bond order of 3. With increase in bond order, bond enthalpy increases and the bond length decreases. Just one second. I think I have a doubt. One second. So you just have to wait for the bond order. I'll explain to you this when we learn molecular orbital theory. That is where it is coming from. MOT. Molecular orbital theory is another theory in which it will become clearer for you why this is 2.5. Okay. So basically in molecular orbital theory, we have orbitals of molecules. We make orbitals of molecules overlap with each other. Now, what is happening here is that you have something known as bonding and anti-bonding electrons. Okay, so it has the total number of electrons that are present in an NO molecule is equal to how much? 15, right? It has a total of 15 electrons. Nitrogen has 7 electrons and oxygen has 8 electrons. So there is a total of 15 electrons, right? There is a total of 15 electrons, right? So there will be 10 bonding electrons and 5 anti-bonding electrons. So bonding electrons and anti-bonding electrons, once you realize what they are, then it will become easy for you. Okay. So we'll continue this when we reach that point. Next point. Now, polarity of bond, the dipole moment. No bond or compound is either completely covalent or ionic in nature. Okay, because for example, you have the HCl, right? HCl is a covalent molecule. Hydrogen chloride is a covalent molecule. But what happens with HCl? Because chlorine has a larger electronegativity, being more selfish, it attracts the bond pair of electrons or the shared pair of electrons towards itself. When it attracts this shared pair of electron towards itself, what is it doing? It is basically make bringing the it is moving the electrons from the center towards itself. Therefore, it is creating two different centers. You have the positive center that is present in hydrogen and a negative center that is present in oxygen. So basically, a covalent bond is having an ionic character, right? It is having an ionic character. Now, the dipole moment is, yeah, see what is happening here. In case of a hydrogen chloride molecule, what is happening? Hydrogen and chlorine are basically forming a covalent bond. Okay. Now, in a covalent bond, what happens is that hydrogen and chlorine will put one electron in the middle, and then they will basically decide to share it. Okay, but chlorine being more electronegative than compared to hydrogen, chlorine being more electronegative as compared to hydrogen, it will attract this pair of electrons, this shared pair of electrons towards itself. Therefore, what is happening here? Look at this. See, so this is hydrogen and this is chlorine. So this lone pair of electrons is much more closer. This bond pair of electrons is much more closer to chlorine than that of hydrogen. Therefore, what happens? There is a slight positive charge in hydrogen and there's a slight negative charge in chlorine, right? So the bond is becoming polar. A covalent bond is becoming polar due to the The covalent bond is becoming polar due to the change in electronegativities between the two. Okay, there is a change in electronegativities between the two. Therefore, what is happening? This bond is becoming polar. So, this polarity is actually creating an ionic character in a covalent bond. So, you are inducing an ionic character inside a covalent bond. Understood this? You are inducing an ionic character inside that of a covalent bond. Am I making myself clear, Drupad? Okay, let's go. Now, so, and it is defined as the product of magnitude of charge and the distance between the charge. Okay, distance between the centers of positive and negative charge. It is usually represented by the Greek letter mu. This is what we have, the dipole moment. Now, mathematically, it is expressed as dipole moment mu is equal to the magnitude of any charge. It can either be positive or negative. I'm saying magnitude because we are not going to include the negative sign. So it has the magnitude of any charge multiplied by the distance between the two charges. For example, if you have a charge plus q here, you have a charge minus q here, both of them have the same magnitude. So Drupad, look at this. Hydrogen and chlorine, when they were sharing this electron, chlorine actually pulled the electron towards itself. So it gained a slight negative charge. But hydrogen will gain the exact magnitude of charge that chlorine got, but it will have an opposite sign, that is a positive value. So when two charges having the same magnitude but opposite signs are separated by a distance d, then the dipole moment mu is equal to qd. Understood? This is what I'm trying to tell you. So the dipole moment is what? It is a phenomenon that exists between two charges having equal magnitude but opposite signs separated by a distance. That is what we call a dipole moment. Okay, the dipole moment is equal to charge multiplied by the distance of separation between them. Now, it is usually expressed in Debye. Okay, Debeys, Debye or Debeys, anything. Okay, I call them Debye because it's pretty fun to say Debye. Okay, where C is the coulomb and M is in meters. So, you are multiplying a charge. Charge has an SI unit of coulombs, and coulombs is represented by C. You have already learned about this in class 10th. Okay, current electricity, you have learnt about this. And distance is measured in meters. So you have coulomb meters. Now, don't accidentally write cm because cm is centimeters. Okay, so always write capital C and small m. It is represented like this, cm. Now, hence ESU is known as the electrostatic unit. Now, C is what? The static coulombic centimeter. Now, it is a vector quantity and it is represented by a cross arrow pointing towards the more electronegative atom. For example, if you have hydrogen here and you have chlorine here, I would create the a dipole having an arrow like this. The arrow points towards the more electronegative atom. Okay, so if there is a change, if there is a variation, or if there is a difference in electronegativities between the two atoms inside a molecule, then there will be a dipole moment. Okay, and the direction of the dipole moment will be from the more electropositive, the more electronegative atom. The dipole moment between in the bond will always have this value. See, What is this arrow showing? It is showing that the electrons that were being shared have moved towards your chlorine. That's what they're trying to tell you. Look at this. See, you have hydrogen, you have chlorine. The shared electrons that were bonded between them are closer to chlorine. That is why we are doing it like this. The movement, the arrow is towards this direction. Next, did you understand this logic, Drupad? Okay. Dipole moment in the case of diatomic molecules. In diatomic polar molecules, the dipole moment of the molecule is equal to the dipole moment of the polar bond. The dipole moment of HCl molecule is the same as HCl bond. Okay, it is 1.07 device. The degree of polarity of such molecules is also affected by the magnitude of their electronegativity differences. Greater the difference in the electronegativity of the combining atoms, greater will be the charge separation, and hence greater will be the polarity of the molecule. You know how to calculate electronegativity, right? Which rule would you use to calculate electronegativity, Drupad? Who was the person who gave us the formula for electronegativity? What was his name? Drupad, what was the Pauling's electronegativity formula. Okay, next. For this is for diatomic molecules. Okay, so he is trying to say that the polarity, the dipole moment between HCl will be less as compared to HF, because fluorine is a more electronegative element as compared to that of chlorine. Okay, did you understand this logic? Shall I move on? Okay, now the dipole moment of polyatomic molecules. In polyatomic molecules, the dipole moment is not only dependent upon the dipole moment of individual bonds but also upon the spatial arrangement of various bonds present in the molecule. Okay, so here the dipole moment is not just the bond polarity, it has to be equal to the various arrangements of various bonds that are present here. You will learn more about this in later. In such molecules, the net dipole moment is a vector sum of the dipole moment of various bonds. Luckily for us, we know how to calculate the vectors, right? Again, in the case of symmetrical tetrahedral and polyatomic molecules like boron trifluoride, methane, and carbon tetrachloride, the molecular dipole moment is found to be zero. For example, you have carbon tetrachloride looks like this. Okay, next you have the boron trifluoride. Okay, and then you have the methane. Understand this very carefully. This is a four marker. Okay, now Drupad, who has more electronegativity come in carbon or chlorine? Chlorine, right? Chlorine is more electronegative. So the for this bond, for this particular bond, the dipole moment will be in the upward direction. For this particular bond, the dipole moment will be here. For this particular bond, the dipole moment will be here. And for this particular bond, the dipole moment will be here. Okay, so the dipole moment is being cancelled out. Okay, this is not the exact structure, it's not a tetrahedral structure, but I'm just trying to explain this to you. Because these polarities, these bonds, these dipole moments are in opposite directions, what ends up happening is that dipole moment of one bond actually cancels the dipole moment of the other. This will cancel the dipole moment of this. Similarly, here boron and fluorine, obviously the direction will be like this. Okay, so we know that the angle between these will be 120 degrees. We just discussed this. 120, 120, 120. Now if we realize them in vectors, what do we get? If we realize them in vectors, we see that this and this will exactly cancel each other out, right? I can even draw you the diagram. Look at this. See, you have one bond like this, you have the other bond like this, yeah, and you have another one like this. So it is forming a loop, and we know that if all the three bonds form a loop, the net vector magnitude will become zero, right? We know this, right, Drupat? In physics, we have learned this in vectors. Okay, so there is no dipole moment here, there is no dipole moment here. However, if the bonds are not identical, the molecules may have a net dipole moment. For example, CHCl3 is also a tetrahedral but has a dipole moment of 1.04 d. The lone pair of electrons also possess some dipole moment, and thus its magnitude and direction also reflect the net dipole moment. Now let us look at the example of CHCl3. Can you tell me what CHCl3 actually is? You should know the name of CHCl3. Yes, exactly. Okay, okay. Now, one of the hydrogen and the other is getting cancelled. Okay, but here what is happening? Carbon is more electronegative, right, compared to that of hydrogen. So the direction will be like this, and the direction will be like this. So these two got cancelled, but there is a net dipole in the downward direction. Can you see this? Can you see the net dipole in the downward direction happening here? That is why you have 1.04d. But see, look at this. Both of them, both these structures are tetrahedral. Both of them are equally tetrahedral, but one has the ability to have a dipole moment, whereas other does not. Okay, let's move on. Now, next, we will look at the case of lone pair of electrons. The lone pair of electrons also act as if they are participating in the formation of a bond. Now, let's actually look at what is happening here. NH3 and NF3, nitrogen trifluoride, both uh, are trigonal pyramidal molecules with one lone pair of electron, but the dipole moment of NH3 is greater than that of NF3. This is because in case of NH3, the orbital dipole of lone pair is in the same direction as the resultant dipole moment of the NH bond, whereas in NF3, the orbital dipole is in the direction opposite to that of the resultant dipole moment and of the NF molecule. This is basically going to be a three marker. Okay, three marker question. Now, this is how the explanation goes. Let's actually draw this. You have a lone pair present like this. Okay, they should have actually taught you this after they taught you valence shell electron pair repulsion theory or the Vesper theory. But what to do? So, let's see this. This is hydrogen. This is hydrogen. Okay, and this is hydrogen. Now, Drupad, why did I draw it like this? I'm drawing it like this because it's like a tripod, Drupad. Okay, see what is happening. Three of the bonds are in the same plane. Okay, but one bond is what? One bond is in a different plane altogether. It's in the back. Okay, that's how a tetrahedral structure looks like. Okay, these two are in the same plane. These two are in different planes. Okay, so let's look at the dipole arrangement that is happening here. Now, here it is positive, negative, positive, negative. This is positive and this is negative, and basically this is pure electrons, right? The dipole moment will be actually like this. So what is happening? There is a dipole happening here, there is a dipole happening here, and there's a dipole happening here. So what happens is they add up, they actually add up. Therefore NH3 has a larger dipole moment. Look at the dipole moment of NH3, 4.90 into 10 raised power minus 30 coulomb meter. Now let us look at the example of NF3. Now what is happening here? You have N, again a bubble. This bubble represents the lone pair of electrons. Again I'm telling you, Drupad. Okay, this bubble, this balloon, can you see the balloon here, right? It represents the lone pair of electrons. You can still see the screen, right? There is no problem. Okay, so here look at this. There is dipole happening here, there is dipole happening here, there is dipole happening here, and there is dipole happening here. So all of them are in different directions. And what is happening even more, that there is a downward direction here, there is an upward direction here. Okay, so this is the reason why they are canceling each other out. So what is happening? The resultant dipole is becoming less compared to that of NH3. In NH3, the flow, all the dipole moments flow was in one direction. But in the case of NF3, all the dipole flow is in opposite directions, right? They are away from the nitrogen. Therefore, what ends up happening? The dipole actually decreases. The dipole moment actually decreases. Understood? Okay. Now, the dipole moment of some molecules are given here. Now the H2. H3 basically there is no dipole moment when you have a symmetric molecule. Okay, for example, H2O2 Cl2. Okay, because all these different atoms, they have the same electronegativity, and when you are bonding them with themselves itself, the bond enthalpy bol raha hoon main, the the what do you say, what was it? The dipole moment actually becomes zero. So in the case of H2, it is becoming zero. Okay. In the case of CO2, we have already discussed this. There is no lone pair of electrons. There is movement in the opposite direction. Now look at the diagram of CO2, and I'll explain this to you why it is not polar. You have carbon. You have double bonded oxygen here. You have double bonded oxygen here. The dipole moment is in this direction here. The dipole moment is in this direction here, right? So both the dipole moments have the same magnitude, but they are in opposite directions, therefore they cancel each other out. Therefore what happens? The dipole the dipole moment becomes zero. Understood? This is why the dipole moment becomes zero. Two equal and opposite forces acting in the opposite direction. Okay, now next, you have the CH4 also we have discussed. The net dipole will become 0. CCl4 also we have discussed. The net dipole will become 0. CHCl3 we have discussed, it will become 1.04. Okay. So, is there any doubt in your mind regarding dipole moment, Drupad? Okay, let's move on. Now, ionic character in a molecule. Okay. Now, in a covalent bond, we want to know how much ionic character is present inside. Therefore, what do we do? The percentage of ionic character can be calculated from the ratio of the observed dipole moment to the dipole moment for the complete electron transfer. That is 100% ionic character. Now, the observed dipole moment will be what? See, basically, let's look at this. You have hydrogen, fluorine. There is actually a sharing of electrons that is taking place between hydrogen and fluorine, right? But the the lone pair of electrons are much closer to that of to chlorine as compared to that of hydrogen. Therefore, there is a slight positive charge and a slight negative charge. Okay, there is a slight positive charge and a slight negative charge. So the dipole moment observed will become equal to what? This delta positive multiplied by the distance. Okay, let's call it d, the distance between them. So this is the observed value. Now, what will be the 100% ionic character? Here you have H, you have Cl. There is a bond here. Now, how did this bond form? Hydrogen actually donated this electron to chlorine. Hydrogen donated this electron to chlorine. Therefore, there is a plus one charge here and there is a minus one charge here. Okay. So, the dipole moment of 100% ionic is equal to how much? 1 multiplied by d is equal to d. Now we know that this delta value is less, much less than 1, right? This delta value is much less than 1. Therefore, the dipole observed will be less as compared to dipole ionic right? Okay, so this is what is happening here. The observed upon the calculated into 100. This is how you do it. Okay, one, you see the sharing that is happening and how much dipole moment is being observed. Second, you actually transfer the electron from the hydrogen to the chlorine, so you will get another dipole. Okay, let's move on. Now, the percentage of ionic character in a certain bond, the percentage of ionic character in a certain bond AB is 54.76%, and the bond length AB is given as 246 angstrom. What is the dipole moment of the AB molecule? Okay, dipole moment. So they have given us what? The this value they have given us, and the bond length. What is the dipole moment? One second. Let's see. If the molecule is 100% ionic, then mu calculated for 100% ionic is how much? Is equal to, you will have 1 plus 1 charge, right? So it will be q multiplied by d. So the charge of one electron will become how much? It will be 1.6 into 10 to the power minus 19 multiplied by 246 into 10 to the power of minus 10. Okay, so this becomes the ionic value, 100% ionic. Okay, this is the 100% ionic value. That is, this value has been calculated. Done. This value has already been given to you. Done. Now you need to find mu observed. So mu observed will become equal to how much? 100% ionic character multiplied by your this thing, mu calculated upon 100. That will become the observed value. ठीक है? Understood, Drupad? Percentage of ionic character. See, percentage of ionic character multiplied by this divided by 100 will give you the dipole moment observed value. Okay, any doubts here? Okay, fine, let's go. You have doubts? Okay, fine. Now the covalent character in ionic bond, called the Pahan's rule. Now we have discussed about the ionic character in a covalent bond, right? We have discussed the ionic character inside a covalent bond. No problem there. You have a selfish atom that is basically holding on to the shared pair of electrons towards itself. Therefore, the bond is becoming ionic in nature. Okay, but what if you have an ionic transfer? Okay, inside an ionic molecule, what is happening? Inside an ionic compound, what is happening? There's an actual transfer taking place, but still there is some partial covalent character to be seen, and that is going to be the Fahan's rule. The extent of purely ionic or covalent bond is an ideal situation, and we know that nature does not have ideal situations at all. Just as all the covalent bonds have some partial ionic character, the ionic bonds also have some partial covalent character. This partial covalent character of an ionic bond was discovered by Fahan in terms of the following rules. These are known as Fahan's rule. There are, I think, four rules of Fahan. Yeah, no, three rules of Fahan. Sorry. Okay, the small size of the cation. Now, the small cations, because of their high electron density, tend to dissociate, distort, or polarize the electron cloud of the anion to a great extent. Hence, the compounds containing small cations will have more covalent character. That is, LiCl is more covalent than NaCl or KCl due to the smaller size of the lithium ion compared to that of sodium and potassium. So, LiCl should ideally form 100% ionic bond, right? Because lithium belongs to which group, Drupad? Lithium in the periodic table, which group does it belong to? Alkali metals. Yeah, lithium belongs to the alkali metals. Now, alkali metals have, they are metals. Metals have a characteristic called electropositivity. They have the ability to lose an electron pretty easily, right? So lithium should actually form the plus 1. Lithium should form plus 1, that is Li plus. But what happens when it forms a molecule? Its electrons are too close to the nucleus because it's a very small atom. Due to this, what happens? I have told you this before also. Now, in a smaller molecule, in a smaller atom, the electrons are present in the inner shells, right? Like you have the K shell or the L shell. So there is not enough space inside the L shell for all these electrons to actually um, stay easily. So what happens is there is a large electron density that is present in these type of metals. Okay, there is a large enough electron density that is present in a smaller metal. Now, this electron dense cloud of this lithium is going to distort. Distort means basically affect. It is going to distort the electron cloud of the anion that is being next to it. For example, chlorine. Now, this does what? This basically allows certain amount of covalent character to be seen, okay, in an ionic bond. Okay, so hence the compounds containing small cations will have a more covalent character. Lithium chloride is a more covalent than sodium chloride and potassium chloride due to the small size of the lithium ion as compared to that of sodium and potassium. So sodium and potassium, because of the larger size, have more ionic characteristics compared to that of lithium. Next, you have, oh no, I was correct. There are four large sizes of anions. Now, larger the size of the anion, greater is its polarizability. So, greater will be the covalent character in that bond. For example, covalent character of lithium halides is in the order of a lithium iodide, lithium bromide, lithium chloride, and lithium fluoride. So, the bigger the ion, more will be the polarizability and more will be the covalent character. So, Drupad, this polarization due to the electronegativity of an atom in a molecule is particularly a characteristics of covalent bonds. But if you have a large enough anion like iodine, the electrons that are present in the outermost shell are loosely bound. So, a strong enough metal like lithium with very high electron densities could actually alter the electron cloud, okay, make it polarized in such a way. So you have what? You have inside a molecule, due to polarization, inside a molecule due to polarization, you are having some covalent character that is present. Okay, I'm sorry if I said molecule, I'm talking about a crystalline solid, an ionic compound. Now, so lithium iodide will have a higher covalent character compared to that of lithium fluoride. Understood? So, Pahan's rule number one, you need to have a small enough cation. Pahan's rule number two, you need to have a large enough anion. Now, here comes rule number three, high charge on the cation and the anion. Higher the charge on the cation, greater is its polarizing power because the cations attract the electron cloud of the anion more easily and strongly. Okay, now hence the covalent character increases. That's why the covalent character of chlorides follow the order NaCl, Mg2Cl2, Al3Cl3. So basically you have AlCl3, MgCl2, and your NaCl. So in the case of sodium chloride, the charge on sodium is plus 1. The charge of magnesium, it is your plus 2. In the case of aluminium, it is plus 3. So as the charge increases, as the charge slowly and slowly starts to increase, we see what? We see that the covalent characteristics is also increasing. Okay, higher the charge on the cation, greater is its polarization power because the cations attract the electron cloud of the anions more easily and strongly. Hence the covalent characteristics. That's why the covalent characteristics of chlorides follow NaCl MgCl2 and AlCl3. Similarly, greater the charge on the anion, more easily it gets polarized. The more negative charge you have. See, what is the meaning of having more negative charge? What is the significance? The more negative charge that is present inside an anion, the higher its chances of basically distorting its electron cloud. See, if you have lesser number of electrons, less distortion will take place. If you have more number of electrons, more distortion will take place. Imagine you are a balloon seller in a field and the wind is blowing. Okay, now you only have one balloon in your hand. There is not much distortion going to take place. Even if the wind blows, only one balloon is getting distorted. But if you have like 50 balloons, or let's say 20, 30 balloons in your hand, then what happens? There is a large enough distortion, right? The whole cloud of the whole basically that balloon's structure basically starts to distort violently as the wind flows. Okay, so the more number of anions, the more number of the if you have a higher increase in the number of electrons in the anions, what ends up happening? Your the distortion becomes more easier. It becomes more easier for the cation to distort the anion. I hope I'm making myself very clear, Drupad. Do you understand this? Did you understand the balloon logic? Okay, so the three Fahan's rule that we have learned till now is smaller cation, larger anion, and the charge on the cations and anions if they are large enough. If a cation has more positive charge and anion has more negative charge, then the covalent character increases. Now, what is the reason for the covalent characters to increase? It's called polarizability. Okay, so if you are able to increase the polarizability between the two atoms in a molecule, then you are able to create more covalent character between them. Okay, next, the electronic configuration of the cations. In case of two cations having the same size and charge, the one with the pseudo noble gas configuration with 18 electrons in the outermost shell has a greater polarizing power as compared to the other with noble gas configuration with 8 electrons in the outermost shell. Understood? So, what does it mean? What does it mean, Drupad? Can you explain this to me? I have explained this to you in multiple this even in structure of atom I have told you this. In case of two cations having the same size and charge, the one with the pseudo noble gas configuration with 18 electrons in the outermost shell has a greater polarizing power as compared to the other with noble gas configuration with 8 electrons in its outermost shell. Can you understand with this? Like, can you explain this to me? I'm asking you this. In the case of two cations having the same size and charge, the one with the pseudo noble gas configuration. What is pseudo noble gas configuration? It is a configuration, basically a fake configuration. It's not a true configuration, it's a fake configuration by actually gaining and losing of electrons. It is not a natural something, it's not a natural characteristics of the atom, it is just something that is happening. Okay, the pseudo noble gas configuration has greater polarizing power. Okay, with 18 electron in its outermost shell. If you have 18 electrons in your outermost shell, your polarizing power actually increases and has a greater polarizing power as compared to others with the noble gas configuration with 8 electrons in their outermost shell. Okay, all they're trying to say is 18 electrons, better polarizing power, 8 electrons, less polarizing power. I hope I have made myself clear. 18 electrons. Um, could be. Uh, see, the d electrons usually do not. You are going. too close into the coordinate bond character, coordinate bond region. Okay, that is something known as the coordination bond. Okay, the d orbital, most of the elements that are present have a vacant d orbital usually go that way. Okay, so you are slightly getting distracted from the actual this thing. So 18 is also is known as a pseudo noble gas configuration, and the pseudo noble gas configuration basically gives you the ability to, I think, what am I trying to say? Just one second. I'll just one second. So, in Fahan's rule, cations with a pseudo-noble gas configuration, Ns2 Np6 Nd10, that is basically what is pseudo electronic configuration? Every single orbital is full. Okay, has a much greater polarizing power than the cation with a noble gas configuration, Ns2 Np6, outer electronic configuration of similar charge and size. So, Ns2 Np6 Nd10 has a higher polarizing power than Ns2 Np6. Why electronic configuration matters? What you said is absolutely correct, Drupad. Poor shielding. The d orbital electrons shield the nuclear charge poorly compared to that of S and P. So what happens, because they have poor shielding effect, the nucleus's effect on the nucleus of the cations effect on the d electron orbit electrons in the anion will have a much more significant. Okay, okay, just one second. Let's actually do one thing. Okay, we will continue with this topic in the next class. Okay, in tomorrow's class, most probably we will be able to continue. I'll explain this to you in much more details. Okay, and we can continue in this in tomorrow. Now, students, I hope you really like the explanation that I'm giving. Okay, I'm trying my hardest to make it as simple as possible. This chapter is pretty interesting. Okay, and if you really like my videos, please do like, share, and subscribe. And thank you so much. And if you have any doubts, please put them in the comments. Okay, and I'll see you in the next video. Thank you.